Okay, so welcome back, and in this video we're going to be looking at the acyl chlorides. That's ACYL chlorides. You'll sometimes see them referred to as acid chlorides, and that's the last functional group we're going to be looking at this week. So you're going to need your notes, and we're starting on page 10. Okay, so this is my acyl chloride functional group. It has an R group, double bond oxygen and a chlorine. So you can see why they were often called acid chlorides, because you've literally replaced the OH group of a carboxylic acid with a chloro group here. Okay, now we generally make them via a reaction with PCl5 and a carboxylic acid. PCl5, I'll remind you, is a very reactive reagent. You've seen it before as a test for an OH group. So when it reacts with alcohols, it produces the halogenoalkane and POCl3 and HCl, and you see the steamy fumes coming off. In exactly the same way, we're going to replace the OH group of a carboxylic acid with this Cl, and that's how I've got that functional group, because that OH group has been replaced with a Cl. We still get POCl3 and we still get HCl as our other products. Okay. These are colourless fuming liquids. They smell very strong. They're also soluble in different solvents. Be careful of this one. We can't dissolve them in water. The reason why we can't dissolve them in water is because they react with water. They're also what we call a lacrimator. In other words, they will make your eyes sting. Okay, so we're going to look at some of their displayed and skeletal formulas. I'm going to start with ethanoyl chloride. Eth, that means I've got two carbons, and the oil chloride is the functional group of the acid chloride. So I've got a double bond oxygen and a Cl, and I'm just going to finish it off with the hydrogens. Okay, so in terms of the skeletal formulas, I've got my two carbons. So that's my line, and then I need to show these bonds here on the end, double bond oxygen and my Cl. Propanoyl chloride, exactly the same idea, double bond and Cl. Notice, a bit like carboxylic acids, there's only one place for the functional group to go, and that is the end of the molecule, because I've already used up 3 of carbon's 4 bonds with the O and the Cl. Again, 3 carbons in a chain, 1, 2, 3, and then I've got my double bond oxygen and my Cl group there. Okay, so the last 3 on this page, you've got 2-methyl butanoyl chloride. Notice again like the carboxylic acids, we number from the high priority functional group. So this is carbon number 1, that makes this number carbon number 2, and that's where the methyl group goes. Benzoyl chloride, again we're coming back to that benzene ring. We would more normally, in terms of displayed formula, show it without the carbons and hydrogens. We show it as a ring, and then we show C double bond O Cl. And last, hexane 1,6-dioyl chloride. The di simply means 2, so I've got 2 acyl functional groups, 1 on each end of the molecule. Okay, so methanol chloride is unstable, so we don't include it in the table, but they generally have a higher boiling point than the corresponding alkane. There's 2 reasons for this. One, you have more electrons because you've got a chloro rather than a hydrogen, so more electrons, therefore stronger London forces. Therefore more energy needed to separate them. Secondly, they don't have hydrogen bonding between the molecules because they don't have a delta positive hydrogen, but they do have permanent dipole. So PD forces also exist between the molecules. So they have those 2 things. So because they've got more electrons, they've got stronger London forces. They've also got permanent dipole forces, which the alkanes don't. So those two things put together means more energy is needed to overcome the intermolecular forces. However, they have a lower boiling point than the corresponding alcohol. The reason for this is alcohols have hydrogen bonding, which, if you remember, is the strongest type of intermolecular forces, and acyl chlorides do not. Okay, and because the hydrogen bonding is the strongest type of intermolecular force, the alcohols will have a higher boiling point. But the acyl chlorides are much more reactive than the alcohols. They are highly reactive compounds. The reason for this is the nature of this functional group. So we've got two very electronegative elements. We've got oxygen and chlorine, both of which are going to be very delta negative, and then we're going to withdraw electrons from this carbon. So this is going to leave this carbon very delta positive and therefore very susceptible to attack by a nucleophile. Also, this is a planar shape because you've got three areas of electron density. The carbon has no lone pairs, so this is a planar arrangement and therefore again very easily attacked. The other reason, and the other reason why this is such a reactive group, is this bond here between the carbon and the chlorine. The carbon's outer shell electrons are in period 2, whereas the chlorine's outer shell electrons are in period 3. That makes this overlap here not very good, and it means that the chloro group here is a very good, what we call leaving group. So it's very easily lost. And that's the basis of all the chemical reactions of the acyl chlorides. They react very quickly by losing that chloro group. Okay, so that's a very short video from today, just looking at the functional groups and the physical properties of the acyl chlorides. In the next video, we're going to be looking at the last section of the notes for this week, and that's looking at the reactions of the acyl chlorides. So until then, take care, stay safe, bye-bye.